So we are doing set notation. Okay, we're going to talk about how do we talk about numbers in different ways. That's our main idea. All right, the first way up here is probably the way you're most familiar with. All right, where we've got a number line, we've got open circles, we got closed circles. So closed circle there at -2. What is that closed circle going to tell us? Equal to. It's equal to -2. I am including the number -2 in my set. What about at 4? What does that open circle mean? Not equal to that one. Okay, we're getting close to, but we're not really getting there. So if I wrote this as an inequality, I would say -2 is going to be less than or equal to x, and that is going to be less than 4. That is rewriting that same exact number line as an inequality. Good there? Next thing we're going to do is called interval notation. This is the important one. The rest of this stuff is good, you should know it, but interval notation is what we really want here. When we write an interval notation, we're always going to include two numbers. You got to have two numbers at least. Okay, sometimes you might have 4, but we're always going to have multiples of 2. We're going to have two numbers. Guess which two numbers we're going to use? -2 and 4. We're going to write it. It looks kind of like an ordered pair. A lot of times students get unsure about what. It's not an ordered pair. It's different. So from -2 to 4, at -2, we're going to include that answer. So to include that answer, we are going to use a bracket. Have you guys seen that before? Okay. So my first class, they acted like some had seen it, some hadn't. But a bracket there is basically like a closed circle. We're including -2. It's equal to. And then at 4, we're going to use a parenthesis because we're not going to include that number. 4 is not included in my answer here because it was an open circle. That is interval notation written in that form. Technically, we could also put interval notation on a number line. This is not something you see often. I just want you to visualize it. So that is exactly the same thing as what's above it, but instead of a closed circle, I'm going to use a bracket. Instead of an open circle, I'm going to use a parenthesis, and I'm still going to shade in between. So that part's the same. Then we've got set builder notation. That's what we described in Bellwood. Okay, so remember what we got. We've got this curly bracket here to represent a set of numbers. The first thing we got to do is describe which group of numbers does it belong in. So we're going to say our x value is going to be an element. The little e stands for element of. I really want all numbers. I'm not talking integers here, right? I'm talking -2. I'm talking -1.5. I'm talking 2/3. All of those numbers. So we're going to say is an element of all real numbers, such that. So we draw that vertical line that just basically breaks up which group you're in, and then what part of the group do you want. So x is an element of all real numbers such that -2 is less than or equal to x is less than 4. So once you got the set builder part correct in the beginning, then from there it's just writing the inequality again. Make sense on the first one? All right, let's go to the next one. X is greater than or equal to 1. So this time they gave me the inequality. First thing we're going to do is put it on the number line. So we're going to go to 1. Open or close circle at 1? Closed. Which way is my arrow going to point? To the left or to the right? Right, because I'm greater than 1. So I'm going this way. I'm going to draw an arrow. Boom. We're good. There is my number line. If I'm doing set builder notation, curly bracket. I got to say which group I'm in. So x is going to be an element. Again, I'm not picking integers here. I'm picking all those numbers. So x is an element of all real numbers such that x is greater than or equal to 1. We're going to be all real numbers 95% of the time. The only time that's different is like in Bellwork when we really were counting out those numbers. Last thing we have here is interval notation. Remember with interval notation, you need two numbers as part of your interval. Bless you. I got one number. 1 is definitely a part of my set. Anybody got an idea what my other number is going to be? Infinity, correct. We're going from 1, comma to infinity. We always go smallest number, biggest number. 1 is smaller than infinity, so 1 comes first. At 1, what do you think? Bracket or parenthesis? Bracket, because it's included. At infinity, bracket or parenthesis? Oh, no, not a trick question. Good thought, though. I mean, you might got always a parenthesis with infinity. That's the key, okay? Because a bracket means you're included. Are you ever actually getting to infinity? Can't get there. It's infinity. You're not going to make it there. We use a parenthesis to show that we're going to get close to it, but we're never going to get there. Make sense? Try that last one. I gave it to you in set builder notation. It's a little bit funkier. See what you can do with that one. Let's see what we got. So we're going to start off by doing our number line and seeing how that works. So, Carol, what did you do on your number line here?
I had an open circle, a negative 3.
Yep.
And then the line goes left.
Perfect.
And then close circle on the 1.
Wonderful. It was less than -3, so she went open circle. It was greater than or equal to 1, so she went closed circle, arrow to the right. Perfect. There's our two. That's our two different aspects on our number line. The inequality part here should be easy. They gave me set builder notation, so remember that's just basically what my interval is going to be. So if you want to rewrite it, great. If you guys remember doing the union stuff and then that's not a big element of what we're doing in this class. So it's not something that you have to be good at. It's weird, I know. Don't worry about it too much. But x is less than -3 and x is greater than or equal to 1. Interval notation. I'm going to have to write two different intervals because I've got two different setups right there. So I need to have two different intervals in terms of what we're doing. What do we got? Somebody have an idea here? What are my intervals going to be? What do you think here, Aaron?
Infinity, -3.
Wonderful. One thing I would change there, everything's right. One thing I'd include, a negative on that infinity because we're headed towards the left. Everything's good there though. We're going to the left. We're headed to negative infinity, so don't forget that. We do definitely want to distinguish the difference between negative infinity and positive infinity. Good. There's our first one. Then I got to write a second one here. Jack, what do you think on my second one here? Perfect. Bracket 1, comma, infinity, parenthesis. We're going from 1 to infinity. We're including 1. We throw a bracket on it. Questions on how we can describe those different numbers? That's what we're trying to do in bell work. We did a little bit different way. Lots of different ways we could do it. Again, the most important one there was interval notation. Cool. That was lesson 1. Let's do lesson 2. Lesson 2 is functions. Okay. Functions you learned in algebra 1. We're not getting a whole lot deeper than what you learned in algebra 1. We're reminding you of stuff. So it says a blank is a pairing of input values with output values. So you got two things and you're pairing them together. Okay, let's say you had two people at school. They like to hang out a lot, maybe Snapchat each other a little bit, hang out on the weekends. They were kind of exclusive. You would say those two people are in a relationship. Same thing in math class, only there are no boats involved. It's a relationship, no boats involved. That's good stuff, guys. That's the best I got. So, yeah, it's nautical humor. It's funny. The set of input values. So normally when we plug into a problem, the input values, the x values is going to be the domain. And the set of output values, the y values, is going to be the range. So we've got these things, a relation. If you take two things, you pair them together, that's a relation. You can have lots of different pairings, that's a relation. All right? But we have a special type of relation called a function. A function has exactly one y value for each x value. Every single y value has exactly one x value. Or I'm sorry, each x value has exactly one y value. Okay? It's hard to understand. If I just said that to you, it probably doesn't make a lot of sense. Now what I'm going to do in the next 4 things is explain that in better. Okay? You kind of remember this. Graphically, we can remember what's a function or not. So looking at this first shape, give me a thumbs up if you think this first shape is a function. Give me a thumbs down if you think it's not a function. Thumbs up. Yeah, get the eyes looking around, see if we can remember. It's a function. That one's a function there in the middle. If you want to get super creative in terms of at the very end what the arrows are doing, sure. But we're going to say that one is a function. Okay. The second one, the W shape. Thumbs up if you think that's a function. Thumbs down if you think it's not. We're getting no's. Okay. If we're saying the second one's not a function, Kendall, why do you think that second one is not a function? Symmetry, yeah, symmetry is not as important in this aspect here, but sure. Somebody remember why this one's not a function? What do you think? Yeah, that would be the thing there. What do we look for here? There's two y values. So she's saying this right here and right there. Like this ordered pair is like 0, 6. I don't know, I'm making it up. And that one right there is 0, 0. See how that x value has two different y values? We don't want that. Okay, we can't let that happen. What was that thing that we talked about when you learned this originally? Vertical line test. Remember, if you drew a vertical line on your paper, if you touch the graph twice, then it's going to fail the vertical line test. If I drew a vertical line right there, I'm hitting two different spots. If that happens, fails the vertical line test. Not a function. Boo, not a function. What do we think on that circle? Thumbs up, thumbs down. Is that a function? No, definitely fails the vertical line test. You can draw any line, and it's going to have two different y values for the same x value. What about this crazy m over here? Thumbs up, thumbs down? Yeah, we're good. And the next graph, draw something that is a function, and the next one, draw a function or draw a relation that is not a function. Let's go to the next one. So we looked at it graphically. Graphically is important. What about numerically? Okay, so now we're looking at numbers. We've got this set of ordered pairs, 3, 6, 5, 6, 7, 6, negative 7, 6. Give me a thumbs up if you think that is a function. Give me a thumbs down if you think it's not a function. We're getting a little bit of both. Sophia, why do you think that's a function?
Because all of the x values have one y value.
Yep. 3, 6, 5, 6, 7, 6, negative 7, 6. If you don't remember, draw a quick picture of that. All right, 1, 2, 3. 1, 2, 3, 4, 5, 6. Boom. 5, 6, 7, 6, negative 7, 6. Is that going to pass the vertical line test? Yeah, it's a horizontal line. The y's repeated all the time. Who cares? I don't care if the y repeats. It's the x can't repeat to two different y's. Okay? Looking at letter B. So letter A was a yes. Letter B, thumbs up, thumbs down. Do you think that one's a function? Yes or no? Again, some saying no, some saying yes. Anaga, what do you think? Anaga. Dang it, I was trying. Sorry, Anaga. Keep doing it. I'll figure it out. Say again, I'm sorry. Perfect. 3, 6 is repeated. It's the same point that's going against. So don't get distracted by that. Okay, some students will be like, oh no, there's two x values that are the same. Who cares? Same y value. That's the rule. The x can't go to different y's. Okay? That's our rule with what's going on there. Make sure we understand that one. That one is a function, because if we just cross out that one that was duplicated, we're still good. We're still good. Letter C. We're looking at that one. Thumbs up, thumbs down. Function, yes or no? Getting some yes, getting some no's. Why no here, Ella? Perfect. 2, 1, 2, negative 1. Same x value, different y value is bad. Not a function. Letter D. Thumbs up, thumbs down. What do we think on D? Herman, why no? Yep. 3 repeats. Oh, just kidding. The 3's repeat to two different y values. Bad. Move on. Questions there? Let's get into some a little bit tougher ones. My students were struggling with this a little bit last period. Examples of equations that are functions. Okay, so think of an equation. If I said you got to graph this thing and it's got to be a function, what's an equation you could tell me right now that would be a function? What do you think, Lydia? Y equals 2x, a wonderful example. That would be a slanted line with a slope of 2. That would be a function. Somebody got another one for me. What's another equation that you could tell me that would work? Anaga? Y equals x squared. Wonderful. A parabola. If I drew a parabola, it would definitely pass the vertical line test. What else? Good news is in a couple days, I'm going to teach you a whole lot more, okay? Yeah, y equals x. Sure, all lines are going to work. We're not going to go to all those. Square root graphs. Do you remember what a square root graph looks like? Cut half of a sideways parabola. This is a square root graph. Is that going to pass the vertical line test? Sure. So y equals square root of x. Y equals x cubed. Anybody remember what y equals x cubed looks like? Yeah, it's this guy. That guy. We'll do it in a couple days. You've forgotten. That's all right. What about this shape? What is this one? A V. Y equals absolute value x. Would that be a function? Yeah, you just got to remember them. Cool. That's not too bad. Now we got to think of equations that are not functions. Talk to your neighbor for a second. Try to brainstorm some equations that you remember, or some shapes that you would think would not be a function, and what that equation would be. What we can do. This is not going to be an extensive list. I'm not putting down everyone that ever existed, but we're going to come up with a couple. Eli, what'd you guys come up with? You come up with any shapes?
A circle.
A circle would fail, right? It would fail the vertical line test. Anybody remember what the equation of a circle is? Oh no. Oh no. You all definitely just said x squared plus y squared equals any number. Remember, you take the square root of that number and it's the radius. Oh yeah, I can definitely see all your eyes light up and totally remember that. That's a circle. It's got a radius of 4. Cool. That would fail the vertical line test. Anything else? Anybody else come up with a different one? What you got? Yes, so I'm going to write it a different way. Y squared equals x. You go with that? She just took the square root of it and she said plus or minus. I just said y squared is equal to x. Same idea though. Does that make sense what's going on there? Do you remember what shape that would be here, Lydia? Yep, it's a parabola tilted. It's a sideways parabola. It would look like that, but better. Other ones. Anybody come up with something different? What you got, Aaron? Oh, the other one. X equals 2. Yes, good. I agree with you on that one. This one's kind of the funky one. X equals Y equals lines. You get to mix them up all the time. Remember, it's whatever line it crosses is how you name it. So if you want to draw a vertical line, it's crossing the x-axis, so it's an x equals line. But yes, good idea. X equals 2. This one's going to be kind of my anomaly here, but that's okay. Other ones. An ellipse. Would an ellipse fail the vertical line test? An ellipse, remember, is an oval. That would look like this. It's x squared over 4 plus y squared over 9 equals 1. Yeah, for sure. You totally could do hyperbolas as well. Remember hyperbolas, it's like x squared over 4 minus y squared over 9. There's a lot of other ones we could do. That's a list. I'm going to take out that x equals 2. What do you notice about those other functions or those other things that make it not a function? The y is squared. That's always going to be a kind of a tip-off point. If your y is squared, okay? If your y is squared, that is a good idea. Hey, that might not be a function because that squared y value allows you to have 2 different y values for a single x. That's what that's coming from. Questions with anything on the front side? There's the last box. It's easy. Let's go to the back side. All right. On the back side, it says the domain of a function is the largest set of real numbers for x, for which the value of f of x is a real number. Okay. I am not a textbook definition guy. It's not something I'm good at. Okay. I could say read that, and you could read it, and then your brain just kind of shuts down. It's just a bunch of mixture of words that don't really mean a lot. Okay. So the best way to think of it is be able to read that, but then be able to explain that in your own words. Okay. Talk with your neighbor for a second and come up what is a better, clearer way in your brain to say, what does a domain mean? So again, just trying to better understand it. And you might not be perfect at it. You might look at it and be like, oh, that makes sense to me. I don't really need to say another word. Or maybe it doesn't make any sense. You couldn't do anything. But just try to be able to think of things in a simpler way is going to help you out. Kate, what'd you guys say? What's a way of you describing domain? Yeah, and that's true. When we talk about x value or we talk about domain, we won't ask you for the domain of non-functions. It's not something we do. That is a question about that. So it's all the x values for sure. Okay, all the x values that you're given there. The one thing I would put in that is that last caveat here, which is important. Okay, all the x values that get a real y value. And what you described is great. Just trying to make sure we understand what's going on there. All the x values that get you a real y value. And If you're just looking at a picture, you wouldn't even think about those. But if you're looking at an equation, that's what we need to look at a little bit closer. Okay, so let's look at these real quick. Okay, we will do domain. Domain will be a common thread through all of first semester. We'll often talk about what's the domain of this function. Okay, so we need to understand that. The first one, I've got 4 parentheses x plus 3 squared. What number could I plug in? What x values could I plug in and get a real number? Could I plug in the number 1? Could I plug in the number -7? I could plug in the number 3,862.5 and be perfectly fine. There are no numbers that I can't plug in, that I can't add 3 and then square it and then multiply by 4. It's fine. Every number I plug in, I'm going to get a number out. So the restrictions here are none. Okay, so what is my domain if there are no restrictions? All real numbers. Every number that I have, I can plug in and I will get a real y value as an output. So no restrictions. There's a lot of other answers here that are going to be restrictions, but for right now, in your brain, think, is it a fraction? Is it a square root? If it's not a fraction or a square root, odds are the domain is all real numbers. Okay, but for right now, if we got a fraction or a square root, now we got to deal with something a little bit different. I've got 16 over x minus 2. It's a fraction. So in my brain, I'm thinking, all right, there's something going on here. What could I not plug into this problem because it doesn't give me a real value? 2. Why does 2 become a restriction here? 0. We can't divide by 0. Okay, so if we see a fraction, we're saying whatever in the denominator is not allowed to be 0. Okay, that's my restriction. X minus 2 cannot be 0, because if it is 0, then I'm dividing by 0. If I divide by 0, then I get undefined. Undefined is not a number. Okay, so it's not part of my domain. And so you could solve for restrictions. I left way too big of a box there in the middle. But my domain is going to be all real numbers. What can I pick? I can pick every single number, but my x cannot be the number 2. Because if it is the number 2, I get 0 on bottom bat. Next one. The square root of x minus 2. Not a fraction, but it's a root. Okay? So on this root here, what can I not take the square root of? Negative numbers. Can I take the square root of 0? Yes, don't forget that. Students often kind of miss that one a little bit. You can't have negative. And so my restriction is going to be x minus 2. And I want to write an equation or an inequality that says I can't be negative. What would I put here? X minus 2 greater than or equal to 0. It's got to be greater than or equal to 0. It can be 0. It can be bigger than 0. It just can't be less. So my domain here is going to be all real numbers. You don't have to write that here with an inequality, but just kind of to follow up what we did with our set builder notation, we're going to go ahead and write that. It's all real numbers, but x has to be greater than or equal to 2. If you don't believe me, plug in a number less than 2. Plug in 1. If I plug in 1, it's 1 minus 2, the square root of negative 1. That's imaginary, not part of my domain. Try the next one. Try that next one without me telling you exactly what the answer is. Think about it and see what you got. So I've got the square root of 4 minus x. It's a square root. So if I've got a square root, Aaron, what's got to be true? Aaron Haycox, what's got to be true here about what's underneath there? Got to be greater than or equal to 0. Good. So she's going to take whatever's underneath there, that 4 minus x, and she's got to say it's greater than or equal to 0. Perfect. Okay, we can't have negative numbers. We're going to set that up. Maybe you need the restriction box here to actually show the work. I need to revamp these notes because it's ugly. I'm going to solve. I'm going to subtract 4. Subtract 4. Negative x is greater than or equal to negative 4. So my domain is I could be any number, but I'm restricted to the fact that x has to be with positive 4. What else do I need here? Less than or equal. I need to flip that sign because when I divide by a negative, I got to flip the sign. And again, if you don't believe me, check it. X has to be less than or equal to 4. Well, what about the number 2? That's less than or equal to 4. 4 minus 2 is 2. Square root of 2. We're good. A number bigger than 4, like 5. If I plugged in 5, 4 minus 5. Well, that's negative. I can't take the square root of negative. I'm good. I followed the right rules. Good there? Last one, I'm going to go quickly. take the bottom. It's a fraction. Set it equal to 0. Actually say it can't be 0. So my domain is going to be all real numbers, but x is not allowed to be what? Kind of. Plus or minus 3. It can't be either version, because if I plug in 3, it gets me 0. If I plug in negative 3 and square it, it gets me 0. Right? Kind of see what we're doing there? We're doing just some basics. Here's what I want you to do. Try one more. Try letter D down below. See if you can handle that one. I've got 5 over the square root of x minus 2. 5 over the square root of x minus 2. Is it a fraction?
Yes.
Is it a square root?
Yes.
Oh, no. All right. So I've got the x minus 2. What has to be true about that x minus 2? It cannot be 0. This can't be 0. What else has to be true about it? Can't be negative. Great answers. Okay, that's can't be 0, can't be negative. Can't be 0 because it's a fraction, can't be negative because it's underneath the root. So x minus 2 has to be what than 0? Just greater. Not greater than or equal to, just greater. So my restriction, it's going to be all real numbers, but x has to be greater than 2. Okay, again, try it. I can't plug in 2 because I get 0 on bottom. I can plug in 3, I can plug in 8, but I can't plug anything less than 2.